Okay, let's revisit the energy transport itself after doing these stationary eddies and transient eddies, and looking at these situations where the transient velocities and transient temperatures have some correlation, negative or positive. So here they are positive, so northward; here they are negative, so going southward. And similarly here, depends on whether you're on this part or this part of the front. So cold, warm, cold, warm. So depending on which way the correlations are, you're going to get southward or northward transport. But zonal mean has to be northward, because that's what the energy constraint requires. So we looked at it in the mean. We looked at annual mean meridional transport in the atmosphere. We didn't say we also averaged this in the vertical, because we are doing zonal mean, vertical mean, looking at northward transport. So we said this is what is required by a radiation balance, net northward energy transport in petawatts, 10 to the 15 watts per meter squared. And this is the so per unit area in the meridional direction. If the atmosphere was dry, that's what we would get in the red line. The latent heat that adds to it, as you can see, subtropical gyres versus the IPCZ and so on, make a big difference in the net total transport by the atmosphere. And then the ocean, which is forced by the atmosphere, is mechanically forced to transport energy. And we will see later on that the so-called meridional overturning circulation, ocean is moving energy from a slightly colder hemisphere to a slightly northern, warmer hemisphere. So from the southern hemisphere to the northern hemisphere, which has an impact on how atmosphere gets organized as well, especially in terms of the rainfall distribution. So looking now at the profile of zonally and vertically averaged meridional transports of the total energy that we looked at here. Oops, let me not go back. In degrees centigrade per meter per second, so we are just putting it in terms of V prime E and V bar E and so on. This is the total here for the annual mean and for boreal winter and summer. In B, we are looking at the the transient eddies, so the V prime T prime terms zonally and vertically averaged. C is the stationary eddies, so V prime E prime bar averaged over time, so V bar star E bar star spatially averaged. So just get used to the idea of bar being time average, square brackets being spatial average, prime being deviations in time, transient eddies, star being deviations in space, being stationary eddies. Transient eddies, stationary eddies, spatial average, temporal average, spatial covariance and temporal covariance. These are the key terms, okay? And finally here in D, we are looking at mean meridional flow. So what is the mean energy that's being transported by the mean? So mean in this case is averaged over either a season, year, or sometimes you can do it as shorter or longer times as well. Okay, under global warming you would probably want to see how it is changing as a trend, for example. Okay, so again, we are diverging energy from the low latitudes. Remember, we are going here from the equator in the middle to the southern pole, southern hemisphere and the northern hemisphere. The data is not always good enough to go to 90 south, 90 north. So for whatever reason, it's been cut off here. So in order to obtain units of petawatts, we have to multiply 2 pi r or cosine phi times Cp times P 0 over G, and then that you will get petawatts, but doesn't matter. So just the shape will not change unless you include details of other things. The values will change. Okay, so as we said before, during boreal winter month, the energy transport is here larger towards the northern hemisphere because the equator to pole temperature gradient is stronger. Eddies and mean will be stronger, whereas the value is smaller here. For boreal winter JJA, you can see that the values are slightly different. So there is an asymmetry in the northward transport of the mean total. We will see why that is later on. So that's the JJA, where the energy transport is smaller in the northern hemisphere, down at 4 meters per second per degree centigrade, versus the southern hemisphere, where it is now close to 10 in these units. Okay, so if you look at the transient eddies, you will see that the winter to summer contrast is larger here than here. Again, this has to do with the land-ocean contrast and the southern ocean. The difference that we saw in this figure here is basically showing up here as well. Okay, so because of the land-ocean contrast, the northern hemisphere has a larger winter to summer contrast. And if we look at the stationary eddies here, so V bar star, E bar star averaged over zonal latitude band and vertical, you will see that the stationary eddies in the south are basically almost non-existent because of this zonal structure and no land-ocean contrast, whereas in the northern hemisphere, the northern hemisphere winter has a very strong stationary eddy contribution, whereas the summer contribution is very small and even slightly negative here and positive there. So this corresponds to the termination of the Hadley cell, which we haven't talked about here yet. We'll come back to that later on. Okay. If you look at now the mean flow, mean meridional flow for the annual mean, the mean meridional flow for the annual mean here, the bold line for the winter and for the summer. So we expect divergence around the equator, especially focused on the ITCZ, and that changes with season. As the sun changes, SPCZ gets stronger, for example, and so on. And this is the annual mean, which shows southward flow, northward flow, and then again the mid-latitude and polar changes. Okay, so that is the nice and good story of energy transport. Make sure you understand the overall story is that we need to move energy from the low latitude energy surplus region to high latitude energy deficit regions, but the details are that the flow is always unsteady, so you always get transient eddies, and it is also related to momentum, angular momentum conservation, making the zonal flows very strong and then becoming unstable. So mid-latitude instabilities create mid-latitude eddies that are very strong, and they are very season dependent because that gradient is stronger in the winter. And the stationary eddies are more related to the land-ocean contrast, which is much stronger in the northern hemisphere than in the southern hemisphere. So we saw that the stationary eddy contribution is very strong in the winter in the northern hemisphere, but basically negligible in the southern hemisphere during both seasons because of this channel configuration of the Southern Ocean. So we will leave it here and then come and look at some parameterization issues for energy transport. But main thing to be reminded again is that when we run a full ocean atmosphere coupled model with land, some representation of vegetation and so on, the model has to reproduce coupled climate has to reproduce, simulate all the trade winds, westerly winds, polar easterlies, ITCZ, monsoons, and so on. So it has to produce equator to pole temperature gradient realistically, and hence it has to have realistic northward energy transport. And there again you will take the model flow fields and split those into transient eddies, stationary eddies, and the mean, and see if the model is doing realistic simulations. What we looked at here are from reanalysis product NCEP NCAR, which we haven't defined yet. Reanalysis is basically where we merge data which are from the past. Of course, data is always from the past, which have gaps in space and time, so we cannot infer everything purely from data. So we blend them with models which are validated and are realistic, and we reproduce blended complete products of all the variables we need, which have no gaps in space and time. There are other issues of whether they will conserve mass, they will conserve energy, and so on, because we are pumping data into a model, so there are issues there. Without worrying all that, reanalysis products are the best dynamic reconstructions of the past climate, which can be used as reality checks for models. So when you run a model free of any blending with data, it does energy transports, and then we have to go and validate these energy transports, not only for the mean but eddies, stationary and transient eddies, and we typically do that by using reanalysis products. Okay, let's leave it there.